Okay, so today we are going to talk about the Black-Scholes equation. This is the equation which is used to price financial derivatives, in particular options. You already have learned in previous lectures about the properties of options and also the properties of portfolio consisting of different types of options. Today we move on and bring all the issues together to find the price of an option. Well, we will see this is not an easy task, but in the end, by bringing all the points together we have talked about, you will see it's possible to understand and possible to do. So first of all, take a look to this graph. This is a three-dimensional surface, and what you can see here is basically the surface that is representing the price of a European call option. So what I'm going to do here, mathematically, I will derive an equation, and this equation describes this three-dimensional surface. And then, in the next class, I will solve this equation. So let me start with the derivation of the Black-Scholes equation. First of all, there are certain assumptions we need. The first assumption is we have to assume a certain behavior or dynamics of the underlying financial asset. So suppose we have an option which is based on a stock, Apple or Microsoft or whatsoever. And I assume that this stock price behaves according to what we call a geometric Brownian motion. So my first assumption is that the stock price behaves according to a geometric Brownian motion. And this looks as follows, this equation or this behavior. It's the change of the stock price. S is the stock price here, and the D means it's the change of the stock price. It's the differential of the stock price over time, Microsoft for instance, and that behaves according to the following equation. There is a constant term, mu times the stock price over time, dt, and a second component, which is sigma, which is the volatility, the fluctuations of the stock price, times the stock times dwt. dwt is a stochastic process or a Wiener process, and we have talked about stochastic processes and Wiener process in a previous class. So the behavior of the stock price over time is modeled by these two components. The first component is usually called the drift, which is, in other words, a trend component. And the second component is called the diffusion. And diffusion means something like volatility. So if I want to illustrate this equation in a graph, well, I can say this is the time, and here we have the stock price of Microsoft. And then over time, you know, the stock price moves up and down with a certain volatility, something like that. And now you see there are different behaviors. First of all, there is a trend upwards, a drift, positive. Then maybe here in the meantime of this time horizon, there's a sidewards trend. And there is maybe then over some time a trend downwards. So the first component models this trend. Upwards, sidewards, downwards. And then we see there is some volatility around these trends. And that is captured by my second component in this equation. So this is a way how we model and simulate then mathematically stock market prices. And on another slide now, you can see there are 4 different figures. And if you take a look to the graph on the top right-hand side, you see there are different blue curves. They look like this. There's volatility, some curves go up and some curves go down. All these curves are mathematical simulations based on such an equation. So they are not real asset prices you can see in the market, but they look like asset prices you can see in the market. And that is actually simulations of this equation with my program in MATLAB. On the bottom graph, on the right-hand side, you see the density of these simulations. And you see the stock market starts at 100, and then there's a density that at some time the stock market goes up, at some times the stock price goes down. So there's a density, the biggest density of the stock market movements ups and down is around 100, the starting point. Okay, so this is the first element we need. What we are interested, however, is in the price of an option. And let me call the price of an option V. V is a function dependent on the price of my underlying stock and time. So what I'm going to do in the next, well, let's say 15 or 20 minutes, is to find a solution, a formula that helps you to compute, to calculate the price of an option dependent on a certain stock and certain underlying. Okay, the first step to find this price is, well, let's compute the total differential of this function, which I don't know at the moment, but I know the function is dependent on two variables, so I can compute the total differential. So compute the total differential of this option price function. We see immediately that this function is dependent on two variables, and therefore what we have to do here, if we compute the total differential, is we have to compute the partial differentials. And there's even more, because the stock, this S, the behavior of my underlying, behaves according to this geometric Brownian motion, and that is stochastic. Yeah, because we have here a stochastic process. And therefore, we have to compute the total differential with a stochastic variable. And the rule which is now necessary to do this is so-called Ito's lemma, or formula, you can say. Ito's formula is telling you nothing else as how to compute the total differential of a function with a stochastic variable. So if you have stochastic variables, you have to use Ito's formula. You cannot do it and compute it like you have learned in mathematics in your first semester class. So how does this derivative look like? Well, it's the change of the option price function, and then it's the derivative in respect of the time t, and it's a partial derivative, therefore del of this function in respect of t times the change of time, dt. Then the next component is the change of my stock price. It's a partial derivative of my function in respect of s, the stock price. And by the way, times ds, this is now the total differential of a function if t and s are deterministic variables. If they are not stochastic, you would stop here and would say, well, that's it. But, as I said, S is stochastic, and it behaves according to equation 1. And due to that fact, and Ito's lemma, we have to add a term that pops up here, which is a new term you have probably never seen if you have not learned about Ito's lemma in one of my previous classes. And that is 1 over 2 sigma square s square, the second partial derivative in respect of s times the change of dt. So this term here, I box it in red because this is new. And most of you have problems to understand this term because this is due to stochastics and it's due to Ito's formula. The sigma square and the s square, they pop up because they are the two elements in my diffusion term that is capturing the stochastics. Yeah? And that's the second derivative, and that is due to Ito's formula. And we have learned about Ito's formula in another lecture, so I will not repeat the key insights here, but believe me, that is now the total differential of my function. For further computation, I will simplify the writing of this equation a little bit. So for these fractions, for the partial derivatives, I just write v, because I calculate the derivative in respect of v, and I compute the derivative of my function v in respect of t. And therefore, I will write this as v subscript t. V subscript t means it's a partial derivative of the function v in respect of t. And I do the same here. I call this v subscript s. This means it's a partial derivative of my function in respect of the underlying s. And I do the same here. This is the second partial derivative of my function v in respect of s. And because it's the second derivative, subscript 2s. To make clear, one first partial derivative, second partial derivative. Okay, so this is the first simplification I will use. And now the second simplification is the following. Here you see we have a ds term, which is the change of the stock price. And the change of the stock price actually behaves according to my equation 1. So what I will do, I will substitute for ds here the right-hand side of equation 1. And then I collect all the terms for dt here and here. And if I substitute equation 1 here, you will see then this times here is also dt term, and I will obtain then a dw term. So I will do this in my next line here. So we have the function of my option. And now I collect all the dt terms. Here's one dt term, which is vt. Then I have one dt term from here, which is vs times mu s, which is the first component of my equation 1, which is dt. And then I have the dt from this last component, which is 1 over 2 sigma square s square vss dt. And I write the dt outside of the brackets. So that are all the dt components. The dt is here, this here, and it's here. But now keep in mind there is one term left, which is this times the second component of my equation. So it's vs times sigma s dwt. So that's it. And let's call this equation 2. That is my equation 2. Later on I will come back to this. Okay, so now we have equation 2. Now the next step is I will design a portfolio. And this portfolio consists of certain financial products and assets. But the key trick is that this portfolio is risk-free. So it behaves like a risk-free bond. So how does the portfolio looks like I'm looking at? Well, let's call the portfolio Y. And inside my portfolio I have 3 financial products. First of all, C1, this is the number of bonds. So I have a bond, B. And C1 is telling you how many bonds in the end I have in this portfolio. And then I have C2 times the stock. Maybe Microsoft, which is in my portfolio. And it can have 1 share, then C2 is 1, or it can have 2 shares, then it's 2 or 3, and so on. So C is the number of stock or shares in my portfolio. So far, this portfolio is risky because stock markets, you know, the stock market can go up or down. It's quite risky. But to eliminate this risk, what I do now, I sell an option. And I sell an option based on this underlying stock price. So it's based on my stock price S and T. This is my option function. And what I hope in the end is that the overall portfolio, Y, consisting of a bond, a stock, and a short sell of an option, is risk-free. What does risk-free mean? Well, let me explain a risk-free bond, first of all? A risk-free bond behaves according to the mathematical description as follows. The change of the bond price increases with the risk-free interest rate R times the initial bond investment, let's say 100 euros, BT, over time T. This equation is a first order differential equation. There's no stochastic. It's deterministic. And the growth of the bond price is just by this parameter R. It's risk-free because the risk-free interest rate is given. And this is a way how to describe the development of a risk-free asset in mathematics. By the way, your bank account behaves like this equation because you have a rate of return, R, every year or every month that is paid on your bank, on the amount which you have on your bank account. So this is the behavior of a risk-free asset. So if my portfolio also should behave like a risk-free asset, well, I can write down the same equation for my portfolio. That means the change of value of my portfolio, YT, should also increase with a risk-free interest rate times the money I have in my portfolio over time, DT. So it behaves like a risk-free bond. That is the key assumption I do. And now what I show in the next step is that this portfolio is risk-free if I choose C1 and C2, the number of assets, bonds and stocks, in a very good way. Okay, how can I show you this? First of all, let's number these equations. The bond equation is now my equation 3, and the portfolio equation is my equation 4. In the next step, I compute the total differential of my portfolio equation here, this on top. So the total differential of this equation on top, so maybe I show you this. Well, this is quite easy. It's the change of my portfolio value, C is a constant, times the change of my bond price, dBT, C2 is a constant as well, times the change of my stock price, and then minus the change of the option price function. Now take a look. The change of the stock price, well, this is what I told you 10 minutes ago, defined in my equation 1. The right-hand side of equation 1 defines the change of the stock price. The change of the bond price, well, this is defined in equation 3. And minus the change of the option price function, well, this is actually the right-hand side of the equation 2 we obtained here a step before on the bottom, my last equation. So what I have to do in the next step here is, well, I substitute in for dB, the right-hand side of equation 3, I substitute in for dST, the right-hand side of my equation 1, and I substitute in for this function my equation 2, the right-hand side of equation 2. And then I bring all the terms together. Once again, all the dt terms and all the dw terms which are reflecting the stochastics. Okay, so let's do this. First of all, C1 times right-hand side R times B dt. But as I told you, I will bring all the dt terms in this bracket. So I write the dt outside the bracket. So that's the first component. Then plus C2. Well, remember and keep in mind equation 1. If you look to equation 1, there is a dt component. And this dt component is mu times st times dt. And then we have to write and copy here minus equation 2, which is consistent of two big components. So maybe I make a new bracket here. It's Vt plus Vs times mu times s plus 1 over 2 sigma square s square VSS dt. So these are now all the dt components. So this term comes from here, from my equation 2. But in equation 2, there's also a dw term. And in my equation 1, there's a dw term. So I have to add here. Now, C2 times the second term of the right-hand side of my equation 1, which is sigma s dw. So I will factor out the dw outside of the brackets. And then I have also a dw term minus here in my equation 2, which is Vs. If you look to equation 2, you immediately see that this is the term that pops up here in equation 2. Okay, and this is the change of my portfolio, Yt. So if you look to this equation, it looks quite messy, frankly, that's true. But now we make an interesting observation here. Well, the portfolio value seems to be behaving according to a drift term, like in my equation 1, this first component dependent on dt, and a diffusion term, risky, stochastics. But take a look to the stochastic, to this second term. This is critical. We see immediately that these two components, sigma times s, they are here and they are here. So there's only one difference. The C2 here and the first derivative, the partial derivative of my option price function in respect of s. Keep in mind, what is C2? C2 is the number of stocks in my portfolio. So if I choose the number of stocks, C2, according to this number, which is the derivative of the option price function in respect of s, which is in the end the slope of this function. I already showed you in the beginning this three-dimensional surface. And if I find the slope at the right point, and if I choose this number, which is reflecting the slope as the number of stocks in my portfolio, then this term and this term is the same. So now you can see again that this component, if C2 is equal to Vs, then the first component and the second component is the same. So in other words, this term cancels out. And that means that the stochastic, the risk, which we cannot describe, I don't know whether the stock market moves up or down tomorrow or in a year. This cancels out of the whole equation. So in other words, my portfolio is now behaving like a risk-free asset, as I already told you in the beginning, by this trick. And the trick is, we have to find the right number of stocks or shares in my portfolio. And this choice is called the delta hedge, which is a hedging strategy in finance. We already have talked about hedging and the delta hedge in a previous class as well. So what I do here is, by choosing the right number of assets in my portfolio, I eliminate the risk, and we call this the delta hedge, and we can see then that this risk is gone. So the equation has now simplified a lot. So in the next step, what I do now is, well, this dyt behaves according to equation 4, right? It's now a risk-free asset. And I can write down, instead of dyt, the right-hand side. So let's do this. It's r times y. But what is y? Well, this is my portfolio. So I use the portfolio equation here. So it's C1 times my bond, C2 times my stock, minus my option function. times, this is y, dt. That's equal. So can you see that here I use the right-hand side of equation 4, and for yt, this middle component, I wrote just my portfolio equation. That is my portfolio equation, which is here now in the middle for this yt. Okay, and now the final step is simple algebra, and then we have the Black-Scholes equation. We just have to simplify a little bit, rearrange, and that's it. The first simplification. We have dt on the right-hand side, and we have dt on the left-hand side. It's positive, so we can cancel on both sides the dt component. First step. Second step. Keep in mind, C2 is equal to Vs. That is what we need and what we have used to eliminate the risk. Now, if we substitute in for C2 Vs, then we have here Vs times mu times S minus Vs times mu times S. So in other words, here we have a plus component, and here we have the same term with a minus sign. Yeah? The minus is here in brackets, so it moves in here, here, and here. So these are canceling out each other as well. Take another look. On the left-hand side, here we have R times, if I multiply the R inside the bracket, C1b. On the right-hand side, we have the same term, R C1b. So I can subtract on both sides this term, canceling out each other as well. So and now, let me write down what remains. Well, here we have a minus Vt. I bring this on the left-hand side. That leads to a plus Vt. And then we have here R plus R times, what is C2? Well, C2 is the derivative times S of my option price function. Yeah, this is R times S times C2, which is defined as the partial derivative of the option price function. So we have this on the other side already, but we have to move also this term on the left-hand side. So take a look. This is also a minus, but if we move the whole term on the other side, it gets a plus. So then it's plus 1 over 2 sigma square S square second derivative of the option price function in respect of VSS. And then the final term is this one. It's R. It's minus R times the option price function. Minus R times the option price function dependent on S and T. And this whole term equals to 0. So what we have derived here is the famous Black-Scholes equation. This equation is telling us in the end the price of an option. But to see the solution and the price of an option, well, we have to solve this equation for V. For my function, V dependent on S and T. So if we solve this function and if we find a solution for V, well, then we know the price of an option. Take a second and look to this box. This is a very special equation from a mathematical point of view. It's what we call a second order partial differential equation. Well, we have partial differentials. We have a partial differential in respect of t and in respect of s, the underlying. We have a second derivative in respect of the underlying, therefore it's a second order partial differential equation. So in the end, the problem we have to tackle to solve Black-Scholes equation is we have to solve the second order partial differential equation. And this is, by the way, a very difficult task. It's not easy to do. But Black-Scholes were the first who did it, and they won the Nobel Prize for solving this equation to find the option price for European or American options. I will not do this in this class to solve this explicitly, because I take a long time also to demonstrate this. I will do this in another class. But what I will do at the end, I will show you the solution on the next blackboard, and then I quickly discuss the key features of the solution, and I will close this class. Okay, so now let me write down the solution of the Black-Scholes formula without computing it explicitly. I will do this in another class. But the solution in the end looks like this. So we are able to compute and find a solution of my option price function, and it looks as follows. It's a stock price today, ST, times the standard normal distribution dependent on a parameter D1, I tell you in a second what D1 is, minus K, which is the strike price of an option. We already have talked about this in a previous class. Then this is discounted with the exponential function with the interest rate R over the time to maturity. So that is the end of the contract, that is today, times the standard normal distribution of this parameter D1. So how does the normal distribution looks like? Well, the normal distribution for a certain x looks like 1 over square root of 2 pi, the integral from minus infinity until x of my normal Gaussian distribution minus s squared over 2 ds. So this is the Gaussian distribution. This is the formula for the famous Gaussian distribution, is this one, this n. And now I have to tell you what is x, or d1 and d2. Well, d1 and d2 is the following term. It is the natural logarithm over stock price in period t divided by strike price k plus R, risk-free interest rate, plus minus sigma square over 2 bracket t minus t, and in the denominator we have sigma square root t minus t. This is the solution of the Black-Scholes equation we derived earlier on the bottom of the previous blackboard. Well, you see immediately that this solution even looks very complex, but I told you we have to solve a second order partial differential equation, which is a very difficult task in mathematics. And therefore even the solution is very complex. But what can I tell you about this solution and the beauty of this solution? Well, there is something really good in it. The point is that all the variables now on the right-hand side are known today. I know the stock price of Microsoft today. I know the strike price because this is given in my contract, in my option contract. I know the risk-free interest rate. That is given to everyone. And I have a certain maturity in my contract. That is determining this term, t minus t. So I have the information here, and I know d1 and that must be d2. And I know d1 and d2, because d1 and d2 is determined by this fraction. And this fraction also consists stock price today. I know the stock price of Microsoft today. I know the strike price given in my contract. I know the risk-free interest rate. I know the volatility of the past. I know the time to maturity of my contract. So you see, all the variables are given. I know d1 with a plus. For d2, I have to do the minus. So I have d1, d2. Then I know the standard normal distribution for d1 and d2. I can do this integration. If I substitute the numbers back here and here, I'm able to compute now the price of a European call option. And so this solution is now the solution of this famous problem, how to price a call option. Well, we can also do this for a put option and any other type of options in later lectures. And now take a look at the end of this class, which was quite mathematically, frankly, to this graph, this three-dimensional function. This three-dimensional graph illustrates in the end nothing else as the graphical representation of this solution formula. It tells you what is the price of an option for different times to maturity and for different prices of the underlying stock market. So take a look to the other classes to see an extension of this Black-Scholes model towards exotic options and other types of financial assets. Have a nice day. Bye-bye.